Do you remember, are you a professor, researcher? Okay.
Comrade. No?
Okay. So here we have Pawel Sobocinski. He's a lecturer at Southampton and he works in category theory and he did a lot of amazing stuff in Petriness, defined categorically, and I suppose this is what we'll talk about now. Thank you.
So thanks a lot for the invitation. It's really exciting to be here, especially since I haven't really touched this stuff for about 2 years because, as I'll tell you, this stuff kind of organically led into linear algebra, which is what I've been spending a lot of time on recently. And yeah, so hopefully we can collaborate. And I'll be able to use this for real world stuff. But yeah, so the idea is basically that in general my research is all about thinking about compositional algebra of interconnected systems. So here you have a picture of a Petri net. Here you have a picture of a signal flow graph, which is something that I've been working on in recent years. And the idea is we want to take a model like this and just cut it up into pieces, then be able to have the mathematics to understand the pieces individually, have operations to glue them back together to obtain the composite systems. But this should be compositional, which means that it should be compatible with the semantics. And so it will turn out that these things are monoidal categories, and compositionality means that there's a monoidal functor from the monoidal category that gives you the structure of the system to the monoidal category which describes the semantics. And yes, and I think kind of compositionality is something that all of you guys care about, which is cool, but actually it seems to be kind of criminally underappreciated in sort of research in general. I think maybe now this is changing. And so what we used it for was we developed a compositional model checking of Petri nets, and that's what I'll also tell you about in this talk, how that works. And by the way, there's a whole trend in systems theory, which is called behavioral control theory, due to Jan Willems, and he's got this paper which is open interconnecting systems, modeling by tearing, zooming, and linking. And even though he doesn't talk about monoidal categories, it's clear that that's really the mathematics. That's what, I mean, if he knew about category theory, then he'd be using monoidal categories. Okay, so you guys know about Petri nets. So some attractive things about Petri nets, of course, there's the intuitive graphical syntax. So it has explicit concurrency, right? If I give you a transition system, then even though the transition system might originate from a concurrent process, you can't see directly the concurrency in the transition system, right? Because you're in some state, whereas the concurrency is explicit in the graphical representation of a Petri net. And yeah, it seems to be going, at least if you look at sort of the kinds of people that are using Petri nets, it seems to have gone through a bit of an explosion in recent years. So it's definitely used in biology, medicine, chemistry, several other fields. And I think that's because, we live in this age of big data, where everyone has lots of data. But once you have data, you need a model to make sense of the data. And Petri nets gives you a methodology to construct models. So why not Petri nets? Well, they're often accused of being non-compositional, but there are actually many algebraic approaches going back to the late 80s. Now, why I kind of went back to the drawing board and restarted was because I thought sometimes they're quite weak on the compositional aspects. When you look at the semantics, so this high-level algebra that you put on your Petri nets, doesn't really work well with the underlying operational semantics. And so for that reason and others, sometimes these things are inconvenient for specifying real systems. There's a lot of work on looking at kind of CCS, CSP, pi calculus like operations, which I think are not particularly well suited, even though they result in some well-known work like the Petri box calculus. Okay, so the talk is going to be, I'll give you an introduction to this thing that I invented, which is Petri net with boundaries. And then I'll tell you about the kind of the main application that we worked on with my colleague Julian and our PhD student Owen. And then I'll tell you about some other stuff. Okay, so the first thing that we did, or that I did, is that I wanted to think of a Petri net as a kind of a string diagram. Now, in order to do this, I had to slightly modify the graphical notation. So this is the classical notation of Petri nets. So places are the circles, some of the places have the black dot, which is the token. Then there's a transition, and you can see, for example, this transition here, when it fires, it consumes a resource from here and here, because that's the arrows leading in to the box. And then when it fires, it produces resources here and here, and that because these are the arrows going out of the box, right? So that's the usual notation. Now, there is an equivalent. I mean, this is the notation that we're going to use, and carries exactly the same information. But now, instead of the transitions being directed, in some sense, the places become directed, right? So each place has two ports to which you can connect links. Okay, and a collection of links gives you a transition. So here, this is a transition which connects to the out port of this place, the input of this place, the input of this place, and the output of this place. And you see that basically it captures the same information as in this notation, but the transition itself somehow is not directed. It's just connected the right way to the in or the out ports of the places. And so what is this Petri net with boundaries all about? Well, the idea is that if you look at a Petri net, when this thing executes, a transition, when you fire it, will consume some of the resources. So the resources are the tokens of the places. So you can think of the places somehow as types. The tokens as resources of that type which are available. And then a transition is a synchronization. Right? A transition is a synchronization that consumes some of the resources and produces some other resources instantaneously. Okay, so the idea is that how are we going to decompose this thing? Well, we're going to think of transitions, or since transitions are kind of distributed synchronizations, we're going to think of a kind of an open transition as a partial view of some synchronization. So essentially, we're going to draw a box around Petri nets. We're going to give ourselves some boundary ports, and then these boundary ports transitions can connect to these boundary ports, just like transitions connect to the in and the out ports and the places. And the idea is that, the intuition you should have is that this is a little Petri net component, and we have a local view of a synchronization. So we know that when we connect to the outside world, there's going to be a synchronization, which the local effect of that synchronization will be to consume a token from this place. And here you see that the transition is connected to the import, so we know we have a local view of a synchronization, and when the synchronization happens, a token will be produced here. So this is the type of the box. So the type of the box is simply the number of ports on the left and the number of ports on the right. So here there are 0 ports on the left and 2 ports on the right, so this is of type 02. And it's important not to think of the ports as input ports as output ports, right? So the left is not input and the right is not output. You see that there is no really any directionality. It's just a convenient way. The left and the right is just it's convenient to compose things with left and right boundaries, right? Just as we'll see in examples. Okay, so there are two operations for composing these things, which are the operations of monoidal categories. So there's this categorical composition, which is synchronizing composition, right, in which we connect boundaries and we sort of complete the information about these partial synchronizations. And there's the monoidal product, which is just stacking, you know, these boxes on top of each other. And if I was going to explain it to sort of process algebra people, both of these composition operations are kind of parallel composition, right? So the first one is with synchronization, and the second one is this kind of a free parallel composition. Okay, so I'm not going to give you, well, I can give you the technical definition, but I think the best thing to do is just to show lots of examples to get a feel for how composition works. So I'm just going to go through these four, and I think you'll have a pretty good idea of how it works. Okay, so here we have the, can you guys see that at the back? Is it big enough?
I can see it.
So here we have in all these examples, the left bit is the same, and it's the bit that we saw before. And we're just going to connect it to different Petri nets on the right here. So you see that when we connect, this partial transition T and this partial transition A will connect together to give me a completed transition now. So here we had a kind of a partial view of this synchronization that when if I had consumed a token, this is a partial view of a synchronization that produces a token. So now these guys are glued together, and now we have a full transition that consumes and produces. And you see similar things going on down here.
So undefined just means you have to check that those that are expecting get hooked up with things that are...
Yeah, so we'll see some examples of what happens. I mean, it's possible that, you see, that in this example, you have a transition which is trying to find some partner to synchronize with. But there is no partner, so what happens in the composition? Well, it's well defined, but that there just isn't a synchronization. It was unsuccessful in kind of finding a partner to synchronize with. And you see that here you have this kind of a similar, you have a similar situation, but here there's kind of a weird dangling transition which is not connected to any other ports. And that results in just a dangling, so this is one of these transitions in the Petri net will just produce a resource there and not consume any resources.
Is this still in one safe?
Sorry?
Is it still one safe then? Because I mean, you could use...
Well, no, so the semantics is one safe, sure.
Right.
So it's, we're not yet talking about semantics, right? This is just structure for now.
Yeah.
So that's the, and by the way, these are, so I'm not going to say very much about it, but this is really the connection with, for example, the ZX calculus and linear algebra. Because this is, this guy, this dangling wire and this no wire, they're two units of two different monoid and comonoid structures. So you have a kind of a red and a green, or a black and a white.
Oh, right.
That's super nice.
So what else happens? So here you have a transition T, which is the guy that we saw before. But you see now, there are two different transitions. And the reason, by the way, for the kind of little vertical bars is so that we can distinguish between different transitions. So here there's a one transition which is connected to the boundary port and to the in port. Here there's another one which is connected to the boundary port and the output here. So somehow this transition here has two different partners that it can possibly synchronize with to produce a complete transition. And it's kind of like acts like a non-deterministic choice, right? So, so by the way, this is the co-multiplication with this is the co-unit of the co-multiplication. And so what happens is that in the composition you take both, right? So you have a one transition which you got by synchronizing T and C, and another transition which you got by synchronizing T and D. And here you already saw we get this UE transition. So here's the kind of a compact closed structure, right? Because so these two partial transitions we had before, it could be that the environment actually makes them the same synchronization. So here's a little transition which is connected to the two boundary ports, and what happens when you connect, you just get a single transition that just consumes a token here and produces one there. And here's the other comonoid, the other comultiplication. So here we just have a single transition, which is connecting to the boundary port and to the two other ports. And in our case, of course, you just have a single transition, which is a synchronization.
So the one on the bottom row is basically a product like Cartesian like, and the first one is like this joint union like.
Yes. So this is, I'll tell you a little bit more. Yeah, we can get into the algebra at the end of my talk at this time, but I mean, I can also talk about it at some other point during the week. Okay, so that was the categorical composition, right? Now the monoidal composition is just stacking. There's nothing really to say. It's simple. So this gives you a prop, right? So it's strict symmetric monoidal category with objects natural numbers, where the monoidal product is addition. And it's a nice sort of high-level modeling language for Petri nets, right? Because here's kind of a textbook example of a token ring network as a Petri net. So you see the idea is that this is the kind of network structure, and this is each process. So process does some execution, then returns a token over here, and so the token gets moved along the network. And of course, the problem with this is that although it's easy for us to see as humans that there are three kind of isomorphic components here connected in the network, right? We don't have an algebra to say this, whereas with Petri nets with boundaries, essentially you do what I wanted to do from the start, right? You just kind of cut this thing up, and you get a whole bunch of individual Petri nets with boundaries. So you get these three guys, which are actually the same Petri net, just in a different state. And then you just have some sort of wiring that's going to create this loop. And so we have an algebraic expression in language monoidal categories, which sort of gives you now this rigid description of the system, right? Because we have the individual simple Petri nets, and then we have some kind of a wiring code to tell you how the whole thing is wired up. And what I really like about this, and this also goes back to work by Bob Walters on the algebra of span graph, is that if you look at the algebraic expression, you can read off the topology of the system from the algebra, which I think is a nice thing. Okay, so let's talk about the semantics and talk about the compositionality. So the idea is that we're going to compile down, so the semantics is going to be a functor from this category of Petri nets with boundaries to this category which I call two-label transition systems. So this is just a transition system, but each transition has two labels. Okay, you have a left label and a right label. The idea is that the left label corresponds to behavior that you see on the left boundary, and the right label to behavior that you see on the right boundary. Okay, so I'm going to explain to you why the semantics of this guy is this transition system. So essentially here, the idea is that well, actually, this is not the full transition system, but it's the interesting part, right? So the interesting part is I can have a token here or a token here. Okay, so this is the state that corresponds to having a token at P. This is the state where you have a token at Q. So now what happens when I can have a token at P? Right, well, I can fire this transit. So this is a partially specified synchronization, right? And but I know what the local effect is, right? So when this guy fires, what's going to happen is I'm going to go to the state where there's a token at Q, right? Because this is the output, this is the input. So when this transition fires, token gets consumed from here and gets produced here. Right? So there's going to be the state change. So the interesting part is, why is this the label? Well, you see essentially what you can see on the boundaries. What is the outside world view of this transition being fired? Well, the outside world doesn't see any action at this port, and that's represented by the 0 here. So there's no synchronization going on at that port. On the other hand, here we know that the outside world will need to synchronize with this transition, and so that's the significance of the 1. Okay, so this is the kind of observable behavior from the point of view of the outside world when this transition fires, and this state change is the internal state change of the system. So it's important that these kinds of transition systems, they're sometimes called reflexive transition systems, because you see every state has this kind of self loop, which is 0, 0, which just means that nothing is going on. Right? I'm not doing anything, and I'm not interacting with the outside world. And this assignment, so we have this category, we have another monoidal category now, where it's also a prop, and the arrows of this category are transition systems like this. And now there is a composition operation which essentially does the product of these transition systems, but the transitions are just the ones where you're successfully synchronized in the middle. Right, so I don't know if I have a slide on how this works. No, I do. Okay. Okay, so this is just what I was saying before. There's also some animation. So I have a token here, corresponds to being in this state. When this guy fires, we can see the fact that the transition fires on the boundary, which is reflected in the semantics by this 1. We end up in this state, and then we go back. Okay, so let me just tell you how this category of transition systems, how the composition works. Well, essentially, there are 2 rules that govern the 2 compositions. Okay, so first of all, the sequential composition. If I have a state change in my first transition system, another state change in my second, then essentially I have to agree on the boundaries, and then I can move together. This is the one kind of product of the transition systems. And you can see here's an example. So here I'm composing a transition system with another copy of itself. So the states are just the products. And now what are the transitions? Well, so for example, let's say if we start, let's say it's at the state 0, 0, then there's going to be a transition 0, 1 to go to this state. And how do we get that transition? Well, there's a 0, 0 transition, 0, 0 loop back to 0 here, and there's a 0, 1 in the second system, which results in this transition in the product. And the reason why that's allowed is because this 0, this is a 0, and this is a 0 here, right? So they agree on this boundary where you connect them. Now the other kind of composition, the monoidal composition, is also kind of like a product, but here instead of synchronizing, all I'm doing is I'm just concatenating, right? So I'm just concatenating the labels. So these labels in general will be strings of 0s and 1s. They'll be binary strings, depending on how many ports there are on the left and how many ports there are on the right. Okay, so what is compositionality then? Well, compositionality means that the 2 ways around this diagram end up with the same result. I mean, so this is just another way of saying functoriality. Right? So I can, if I want to work out the state space of a composite net, then I can just compose directly, get the semantics, but I can also use the fact that this composite net was constructed by sort of gluing together two simpler Lego blocks. I can work out the transition systems individually and then compose them as transition systems and go around these two ways as equivalents. And this is really kind of where you can start being smart, because okay, so in general we're interested in if we're interested in the behavior of a net, we're interested in analyzing this guy. Okay, now this guy gets huge, obviously. So as your net grows, the number of states, the complexity of the semantics gets exponentially large. This is the famous state explosion problem. So once you have compositionality, you can take advantage of the fact that you have a structural decomposition of the net. You know what the kind of local transition systems that can be composed to give you the global one look like, and you can be smart about what you do here to avoid building this entire state space. And that's essentially the smart thing of, this is where the idea of compositional model checking comes from. Okay, so I'll just give you an example, right? So this is one of my favorite examples, although it's not the most impressive example. But this is this is a Petri net. It's another standard textbook example. And let's say we want to ask whether it's possible to get from this state, so in this state all the places at the top are marked, to the state where all the places at the bottom are marked, right? So we can start firing. And yes, indeed, this was possible. Now, the interesting thing about this net is that, you see, it's very irregular, right? It's been constructed clearly it can be constructed from simple pieces plugged together. Now, the interesting thing about this is that as soon as I add another bit to it, the path from the start to the end doubles. Okay, so as this net gets larger, the cost of just running the net and exploring whether the state is reachable grows. And there's even more interesting examples where this is double exponential, etc. Right? So you can construct all kinds of weird examples. And so we're going to use the fact that we have a nice decomposition of this, right? So this is the basic building block essentially. And to create this guy, which is just my way of drawing the net from before, well, I just compose this guy 4 times, and then there's these kind of bookend Petri nets, bookend PNBs, which just close the system. Okay, and this is a slightly extended syntax because now I'm marking the start state. I'm putting a token at the initial marking, and I'm also shading the place where I want to get to. Right. So if you think about it, the reachability problem itself is local, right? So because the starting global state is just a composition of the starting local states, and similarly with the desired state. Okay, so now the transition system actually becomes a kind of an automaton, right? Because we have a start state, we have a final state. This is now a non-deterministic, in general, finite state automaton, and the labels, they capture the interaction patterns that essentially allow the component to reach the desired local marking. And so reachability reduces to language emptiness, right? If we don't have a path to reach the final state, exactly when we don't have a path to reach the final state exactly when the final state is not reachable. So what are some of the so by the way, so this algebra is very it's compositional in more ways than one. It's compositional in the sense that, as I said, the assignment of semantics to Petri net structures is functorial, but more than that, various kinds of process equivalences are congruent with respect to the operations. So one thing you can say, one thing you can prove, which we proved in one of our papers, is that weak language equivalence is a congruence with respect to composition operations. So weak language equivalence, what that means is it's language equivalence, but you ignore the 0 zeros. So you kind of you consider 2 words to be the same by ignoring kind of the sign. These are intuitively, these labels is you're not doing anything, right? So you're not seeing any state change. And so we can use this up to weak language equivalence to just aggressively discard irrelevant local states. Okay, so I'll tell you.
What's a tau move and what's an epsilon move?
Okay, so this is what we call the tau move. So the tau move is essentially like an internal. Well, because actually 0, 0 so in this particular case, the 0, 0 corresponds to the net actually doing nothing.
Yeah.
Right, but there are other kinds of 0, 0 moves where the net is doing some internal computation,
Yeah.
but you're just not seeing the outside world doesn't see it.
Yeah.
And in that case, we don't need to know about it.
No.
Right?
So you call those epsilon.
So that's an epsilon move, yes. So we want to. Well, that's it. I mean, in automata theory, these things are called epsilon moves.
Okay.
Here we call them tau moves. But when you think of them as automata, these are really like epsilon moves in automata.
Yeah.
So basically, you can get rid of the internal brain farting.
Exactly. Yes, and this is where all the power really comes from, right? Because I'll give you an example. So, and this is also going to be an example of a situation in which the way you compose changes the complexity, right? So this is somehow the work you need to do is not associativity doesn't hold here. Right, but I'll give you an example, right? So here we're going to compose from the right. So as transition systems, these 3 bits give us these 3 automata, right? But this whole composition, when you do it, it's just weak language equivalent to just the always accepting automaton. Right, so what this means is that basically this Petri net can locally get itself into an accepting configuration without any synchronization on the outside, and moreover, if the outside wants to synchronize, then it says, fine, I can synchronize with you, and I can still then get myself into an accepting configuration. So this is exactly what. So basically, this whole complex behavior, which has 4. Again, it's not that complex, but I mean, it would get more complex as I added more bits. Reduces just to the thing that says I'm always just accepting. Right? This is the weak language equivalent. And so very quickly, if you compose this guy from the right, you'll see that as you compose and you reduce with respect to weak language equivalence, you're just aggressively throwing away the states. So so it's kind of like a fixed point of this procedure. And so this is you can already see this as a kind of a proof of reachability for this whole class of examples, right? Because this is a fixed point. So but if I add one more bit, I'll reduce to the same automaton, right? So I've reached a fixed point. And here's kind of the intuition, right? So this was our original Petri net. We've cut it in 2, and then we ask ourselves, what are the interaction patterns that this guy needs to see on his boundary in order to be able to get itself locally into an accept state? And it turns out that, as we saw, this guy can reach the desired local marking, but also interact as much as it wants with the outside world. But if we were composing from left to right, it actually turns out to be a little bit more difficult, because it turns out that this guy needs to fire twice. So this left part of the net needs to synchronize on his boundary twice, right? So you see that essentially, if you grow it from the left to the right, the state space will increase, right? Because we need to essentially remember how many times I need to synchronize on the boundary. And this is this idea this idea of composition with respect to performance. It's not an associative operation. Okay, so we've got an implementation of this, mostly written by Owen. It's a little Haskell implementation. The tool is called Penrose. We don't really. There's almost no optimization, right? So we try to keep automata small, and then we use this some tricks developed by Richard Mayer and Lorenzo, I think his name is, Clemente, he's now in Warsaw. They had a really nice paper at Popple 2013. We have some memoization, and then the NFA equivalents, we use some work of Filippo and Filippo Bonchi and Damien Pous. And so, of course, on the kinds of benchmark examples which are which are structural, which are clearly structural, we of course kick ass, right? Because we were able to use compositionality, right? So we did a whole bunch of experiments, and in this, we can check that of course, because we reach a fixed point, right? We can basically go arbitrarily large, right? So of course, if you make this buffer example, for example, large enough, then every other tool nerf is going to time out very soon because they try to build the global state space. Whereas we're doing this kind of this compositional approach, right? And obviously, it takes no time at all.
But you have to specify the direction of composition before doing that.
Exactly. Yes. So this is where this. So we have this big impressive table in which we beat everything else, but it's in a sense it's not an even playing field, right? Because these guys, as their input, they take the composed Petri net. What we give Penrose the description of how you should decompose this net.
Yeah, okay.
And then write for the decomposition, right? So
the smart part is already done.
Well, we think, okay, so that's, I think a lot of people were kind of a little bit pissed off at us because of this, right? But actually, if you think about it, the world as it is, it's not a random spaghetti Petri net, right? The world itself has been constructed by connecting things together, right? So why should we not use that information? It's true that the question of how to get the most efficient decomposition is an interesting question, but it's a question we should be asking ourselves anyway. Right? We shouldn't be trying to build tools that work well with this spaghetti world that we just input monolithically. We should be thinking about decompositions.
This is a good point. There's more to say here. So, in your original description, you talked about having a big net and cutting it up.
Yeah.
And I think actually, you could even reject that because you should not, think of the big thing as some arbitrary thing given to you. No, what happens is whoever described this net for whatever reason they had, they wrote it down from the simple components gluing it together. So a criticism of you might be that you're cheating because you're not doing the cutting up work, but you shouldn't have to.
No, but
you should really think of it as building it up rather than cutting things down.
But I think, by the way, that this idea of building things up and also cutting things, there's some really deep research questions there to start with. Because, for example, this non-associativity idea, right? So it actually matters which way you compose. And, we thought about it a bit. I mean, there are some kind of, there's an art doing this. But I think there should be some theory about what's really going on here, right? Like what are the mathematical principles involved?
Okay.
There's maybe one further comment on it. So one thing we did was why we wanted to have compositions, because you can have a library of nets which are pre-analyzed.
Yes.
And then you can just take the
But again, that's my point. You don't start with something big and cut it up.
Well, that's the
start
second
with a little
point.
library.
Usually you
glue it
don't.
together.
If you're building it from scratch, you start. But if you're a company and you have a lot of data already, events, then you can do process mining, you get the big thing, and then you want to cut it up.
Yeah, but there is another question about it. I understand that finding the best decomposition is a non-trivial problem. But is there a recipe to build your Petri net and deriving the right associativity to test the space while you do it?
Well, we were thinking about building such things, right? You can start thinking about sort of a tool which starts exploring one decomposition, gets stuck, and then rebalances the tree, right?
Because
associates the other way.
Pre-analyzed components is totally useless because when you merge them together, the state space will still explode if you don't have a way to build the order of analysis.
Properly, right.
Yeah.
So it's both important.
Yeah, but this should be human-computer interaction, the way it should be. This is the human doing the thing the human is good at, the computer doing the computer is good at.
We're thinking about you saving the situation with open games.
Maybe the stuff that Anthony is doing is relevant to this as well, because it's like adaptive evaluation. So maybe cut it in the middle, you see oh no, this is too big, and you cut it 1/3 to the left or 2/3 to the right.
I mean, it sounds like it's related. And by the way, if you guys are interested, so I already sent this to Fabrizio, but if you look at Owen's thesis, we have there's a whole chapter in which we just take a whole bunch of benchmark examples and basically break them up into bits and then figure out what's the efficient.
Actually, I didn't share that thesis because I don't know if I was allowed to. Can I put it on the mentally ready?
Yes, sure. That's
Okay,
fine.
I will in 5 minutes time.
Okay, so this is exactly what we were just saying, that our tool takes in the algebraic decomposition as an input. There is this, by the way, there are these questions. I also was discussing this with you guys before about you can actually think of, so ignoring that associativity issue for now, there are some graph topologies which just do not admit efficient decompositions. Right? So this is related to these notions of rank width and graph theory, etc. And of course, as we said before, associativity matters. And this is, of course, my retort. This idea is that high-level system descriptions are all given to you, right? So why would you throw this information away and start with a monolithic state space? It just seems like a silly way to go. Okay, so I'm basically almost finished. So this is what my current PhD student is just finishing up now. This idea of, in general, looking at string diagrams now and thinking about how to define the notion of complexity, of structural complexity on a string diagram. So what is it? So essentially, when is a string diagram, when is the topology of a string diagram amenable to an efficient decomposition? And this connects with the paper that Jules, you cited, because we have a particular category of graphs in which this string diagrammatic notion of complexity, which we call monoidal rank, corresponds to rank width. Oh yeah, and this is just one slide. I don't want to get very deep into it now, but maybe if you guys are interested, we can come back to it later this week. So essentially, when I stopped working on Petri nets, I wrote a paper in which essentially I showed that every Petri net can be constructed from this small number of building blocks. Okay, and so you've got essentially a building block for a place, and then all the interesting information comes from the wiring of the transitions. And so you have here one pair of comonoid monoids and another pair of comonoid monoids. So let's forget about the way we draw these pictures now and think about these as generators. Now, can I find a set of relations that's going to generate this? What is the symmetric model of theory here? What's the presentation in terms of generators and relations? So we tried for a bit. It's a bit messy. Maybe I should come back to this now. And we are kind of coming back to it now from a few different angles. But the thing that we did was, okay, forget the complexity. Let's just write the equations how they should be, right? In a more beautiful world. So let's fix Petri nets to make them more beautiful. And what came out was linear algebra. Right? This is the birth of graphical linear algebra. Because graphical linear algebra, you have this is the black structure, the white structure, and when you just write the axioms of Petri nets as they should be in a more beautiful world, they become linear relations. That you have.
As an aside, so one way we were executing these things a few years back was just use sparse matrix multiplications on like a vector.
Yeah, so there's linear algebra lurking in the background. And also just in Petri. I mean, there were also linear algebraic methods developed for Petri nets before, things like place invariants and transition invariants.
Exactly.
But yeah, you can kind of you can really see this transition from Petri nets to linear algebra. Just throw in a few extra equations at this level, and suddenly you've gone from a Petri net to a linear relation.
This is how linear was born.
This is how linear was born. Yes.
Wow.
That's pretty cool.
You buried the history a bit, though.
Well, it's kind of a weird story, It's no. So I originally visited Filippo. I think it was in 2013, and we started thinking about this, and then those 5 years old was studying his PhD. We wrote it down on the board, and we said, forget about this. Let's just write how it should be. Then we didn't know for some months what this was, and it turned out that this was linear LZ2. So it was linear relations over the two-element field. Yeah, so it's like, what's going on? And then I put the next part of the story is even funnier, right? So I got really excited about this. I took a photo of it and put it on Facebook. I don't know why I did this, but within minutes, Bob started chatting to me saying, hang on, this is just the ZX calculus, this is phase free ZX calculus, But, oh my God, what's going on?
And it's over Z2 because it's one cell? Or
Yes, right,
Okay.
yeah.
Yeah.
So basically 1 plus 1 is equal to 0, yes.
so can you do this also for n?
Yes, sure.
Yeah.
That's what we did next, basically.
So for an arbitrary cyclic group, like Zn,
Yes.
this works smooth. And
This
also
works.
your
And so if you do
decomposition
it over
stuff works. Like the equivalence with the automaton, I suppose that instead of 0/01/01, you have like 0n minus 1.
Exactly, yes.
slash-
And in fact, this was also so I mean, all of this was done in this talk for these one bounded nets, right? So we only allowed to have one token at most in each place,
Yeah.
but this generalizes to arbitrary Petri nets. But I think the bounded case is more interesting from an implementation point of view, right? Because
For sure.
So,
Also from a blockchain point of view. One more comment on if I may, on the decomposition. So there's two, like you can either glue on the transitions or you can glue on the places. So I think the framework with the Pollard and Base is gluing on the places. And I tried gluing on the places as well, but on transitions it's much nicer. So I
well, I
cannot.
think somehow it gives you some more flexibility, right?
Yeah.
Because things like, you have, also this is in Owen's thesis, but we also have a paper on archive called Decomposing Petri nets, in which we look at all various, topologies and find clever ways of decomposing. So for example, something like a click is actually a very simple decomposition, right? Because you take advantage of the fact that you're composing in transitions.
And in ICA, so the reason I started looking at the time at ICA Best, this box algebra thing, is because, think about it, you have at the low level, you have an execution of some process. And if this is, let's say, life insurance of a company, and there's hundreds of customers having this life insurance, maybe I want to change my process. Now I need to move all the customers from version 1 of my process to version 2, so you can need a map like this.
Mm.
But now the change has to happen sort of one level higher, because two more fits in. And that's like, it seems that you can find some sort of function between two terms of such an algebra, such that you can lift, quote unquote, the executions to that thing. Do you understand what I mean?
I think so, yes.
So
I think it's about like a dynamic reconfiguration of the topology of the system. Is that?
Yeah, so if I change my net, so maybe I add the transition, I add the state, and I already have executions of this net. I want to move them forward to that thing. So this is like one level higher morphism.
Yeah. No, that sounds really like. I mean, I think this is something that we could do in this framework.
Yeah, that's very cool.
And by the way, I mean, we had a lot of fun just when we were doing these kinds of things, especially with benchmark examples. We had a lot of fun taking these benchmark examples and finding out what are the right building blocks and how to chain them up. So this is like software, some kind of idealized software engineering, right?
I mean, I
just have a question about this. Basically, you showed here that there is a wise way to compose this and an unwise way in which the state space explodes.
Yeah.
But this, I suppose, is dependent on the starting and target situation. So if you want to check if you can reach a state in which the first one is up and the 3 weak ones are down, probably the decomposition you will have to do could be different.
Yeah, because the weak language equivalents will be different, right? So
exactly.
you'll throw away different internal states.
Okay, so it's really like art. You have to do it for.
Well, I don't know. I mean, we didn't get much further than just some basic heuristics. But I think this is kind of a deep research field waiting to be explored.
I'm pretty sure the Anthony stuff could be booming on this.
Seems pretty relevant. We'll be here tonight.
Okay, I think that's really pretty much everything I want to say. But yeah, if you guys are interested, I can tell you more about the Petri net to linear algebra story at some point during the week.
If you ask me, please don't stop. This is dope.
Well, okay. I think it's probably time for a break, no?
Yeah, for now. Yes. Thank you very much.
Okay, cheers.